Hi guys. So let's look at this problem. This is an elemental analysis problem, the combustion analysis problem, and you're being asked to find the empirical formula, the molecular formula. And what are you given? You are given the weight of carbon dioxide in grams, the weight of water in grams, and you're given the weight of ammonia in grams, and the weight of the sample in grams. And of course, there's a large excess of oxygen as well. And so how do you find the empirical and the molecular formula with all these given weights of carbon dioxide, water, ammonia? So first of all, in order to understand this problem, it's very important you understand the elemental analysis. I have explained this in one of my previous videos, but I'm going to repeat this again. So this is what they do. They take the sample, which contains carbon, hydrogen, and any other elements, and they blast them with a lot of oxygen in a furnace. In other words, they are heating it at a very large temperature. So the sample begins to decompose, and the liberated carbon combines with oxygen, gives carbon dioxide. Water is formed when hydrogen combines with a large excess of oxygen. So water and carbon dioxide get absorbed in the absorber chambers, which contain magnesium chlorate and sodium hydroxide. Any remaining gases are then treated separately. So this is the setup of elemental analysis, and this problem relates to that. So generally, we use this with the organic compound, especially when you're making a small molecule compound and you want to know whether the molecular formula is the right formula that you have or that you see from other sources. So anyway, so these are your given. First, always write down. So you're given the amount of sample, amount of carbon dioxide, amount of water, and the amount of ammonia in grams. So first write down that what is given. Next step is write down what do you know. You know already how to calculate the molar mass. So here you are going to write down the molar mass. Just write these down on separate place. Carbon dioxide, the molar mass of carbon dioxide, the molar mass of water, and the molar mass of ammonia. Okay, so write that down on the side. So we find that the carbon dioxide, the molar mass of carbon dioxide is 44 grams per mole. The molar mass of water is 18 grams per mole, and the molar mass of ammonia is 17 grams per mole. Okay, so I'm assuming that you know how to calculate the molar mass. So I'm going to move forward because it's going to take it's a long video. So next is the mole fractions, or the mass fractions rather. Now, what is the meaning of mass fractions? How much of carbon is present in carbon dioxide? The mass of carbon in carbon dioxide. Okay, so that is the mass fraction. So in other words, this can be used as a conversion factor. Mass fractions. So mass of carbon, 12 grams of carbon is present in 44 grams of carbon dioxide. Similarly for hydrogen, 2 grams of hydrogen, because there are two hydrogens. 2 grams of hydrogen is present in 18 grams of water, and that's the molar mass of water. And the mass of ammonia is 17 grams. The mass of nitrogen is 14 grams. So 14 divided by 17, that is the mass of nitrogen in ammonia. So these are going to be used as conversion factors. Okay, so these will be used in conversion factors. Now, how are we going to do this? So this is your known. Okay, now these are the steps that you're going to take. And I have listed 10 steps. Okay, I am using this book, this sample, this problem is coming from the book, the Zumdahl book, and I like to give credit to the authors. So because, writers, they work very hard and bring all this good quality material for us. So this problem is from this book called Chemistry. Okay, so anyway, so here, these are the steps. So the very first step is the mass of carbon, the amount of carbon that is present in carbon dioxide. You get that in grams. Next is you are going to take the grams, the mass of the carbon that is present in carbon dioxide, in the given amount of carbon dioxide rather. In that given amount of carbon dioxide, you get that's going to give you the mass of carbon in grams. Similarly, in the given amount of water, mass of hydrogen. In the given amount of ammonia, mass of nitrogen. Okay, so you get these. Next, you're going to look at the percentage. It's a parts to whole. So the small part is the mass in grams of carbon over the total mass of the sample. Okay, because the carbon is coming from the sample. So the mass in grams of the sample divided by the mass of the sample in grams. Next is the mass of hydrogen that you obtain over the mass of the sample in grams, and then comes the mass of nitrogen over the mass of the sample in grams, and all of these three are multiplied by 100 and you get your percentage. Now we know percentage is 100 and there's a small parts to it, so you convert these percentage to grams. So in other words, if let's say you get 2% carbon, it would mean 2 grams of carbon. Okay, similarly, you convert these grams to moles. Next is you're going to do mole to mole ratio. Next is you place the moles under the respective elements and you get the empirical formula. Then you find the empirical formula mass. Then you find the molecular formula by using the formula, the empirical formula times N. And that N is the formula unit, right? So that's the given molar mass that is comes in the question divided by the empirical formula mass, and you get the formula, molecular formula. So this is going to be your steps to solve this problem. So let us do this now. So I've already done this part. Now I'm going to start the first one. The first step is finding the mass of carbon in carbon dioxide. So our step one is mass of carbon in carbon dioxide. And what is that? The mass of carbon is, the carbon dioxide given to us is 0.1638 grams of carbon dioxide. How much of carbon does this contain? So we know that 12 grams of carbon is present in 44 grams of CO2. So that was your conversion factor. And that's going to give you 0.04470 grams of carbon. Okay, so that's one thing. So you write down, whatever numbers you get. So don't round up or round down it yet. Okay, next is the mass of, then comes the mass of hydrogen in water, in the given amount of water. And what was that given amount of water? The given amount of water was 0.1676 grams of water, okay, times there were 2 grams of hydrogen present in total 18 grams of water. And that is equal to 0.01875 grams of hydrogen. Okay, next is the mass of ammonia. So next comes is the mass of nitrogen, in the given sample of ammonia. So we have now here 0.0633 grams of ammonia. This is that we obtained from the furnace, and that is containing 14 grams of nitrogen is present in 17 grams of ammonia. And this comes out to be 0.0521 grams of nitrogen. Okay, so now we got these nitrogen, hydrogen, and carbon from the carbon dioxide, water, and ammonia. But that is from this. But how much is it in the sample? Now we're going to look at the mass percentage. So the next step is, this was the first step. Our next step is the mass percent. So our second step is the mass percent. Okay. Now we are given the total sample. The total sample is 0.1156. Okay. So my mass percentage in the sample, and that sample is 0.1156 grams. Okay, so now we're going to look at the mass percent of carbon. Okay, mass percent of carbon is we obtained 0.4470 grams of carbon. So just put that 0.4470 grams of carbon is present in 0.1156 grams of that sample. Okay, and since it's a percentage, so times 100%. And here this gives you 38.67%. Let me write it down a little bit lower. Okay, so the carbon is 38.67% carbon. Okay, then comes the mass percent of hydrogen. Then the mass percent of hydrogen. And that mass percent of hydrogen is 0. So the hydrogen is 0.01875. So 0.01875 grams of hydrogen. Okay, and this is going to be present in 0.1156 grams of sample. Okay, times 100%. Okay, so this gives you 16.22% hydrogen. Next is the mass percent of nitrogen. How much is that? So that is 0.0521 grams of nitrogen is present in the total gram sample, 0.1156 gram sample. Okay, and this is times 100%. Okay, and this gives you this is giving you just that. Okay, so now we got the mass of nitrogen, mass percentage of nitrogen to be 45%. Okay, so we have nitrogen 45%, hydrogen, let's write this down. So nitrogen, so carbon is 38.67%, hydrogen is 16.22%, and nitrogen is 45.07%. Okay, so this means this is equal to, if the whole sample is 100, this means that 38.67 grams of carbon is present, 16.22 grams of hydrogen is present, and 45.07 grams of nitrogen is present. Okay, now we have these grams. Now we are going to find the moles. So we are going to next is convert the grams of each of these two moles. Okay, so now we are going to look at the carbon is 38.67 grams times its moles. So we know that 1 mole of carbon from the periodic table, it is 12 grams of carbon. And when you do 38.67 times 1 divided by 12, this gives you 3, actually it's 12, let's do more exact numbers here. It's 12.01, 12.01 grams of carbon. Okay, and that gives you 3.220 moles of carbon. Okay, all right, next is the hydrogen. So this was carbon. Next comes the hydrogen. The hydrogen is 16.22 grams times 1 mole of hydrogen over 1.00 8 grams of hydrogen. So this whole thing comes out to be 16.09 moles of hydrogen. Okay, next comes the nitrogen. The nitrogen is equal to, so we have 45, okay, 45.07 grams of nitrogen times 1 mole of nitrogen is 14.01 grams of nitrogen. And here you get the weight. Okay, so for the nitrogen, 45 divided by 14, 3.220 moles of nitrogen. Okay, so now what you're going to do next is going to be your mole to mole ratio. Okay, so that is next step, which is you're going to take, okay, so this is 16.07, this is 3.220, this is also 3.220, so basically 3.220 is the lower number. So we are going to next do the mole to mole ratio of carbon, hydrogen, and nitrogen. And here we have carbon 3.220 divided by 3.220, and this comes out to be 1. Hydrogen, on the other hand, is 16.09 divided by 3.220, and this comes out to be 5 when you do solve it. Nitrogen is 3.220 divided by 3.220, and this is 1. Okay, so with that said, now we can write the empirical formula because all these numbers are whole numbers already. If they were not whole numbers, then we are going to multiply by with some integer in order to make them a whole number, or you can, if you know, round up a little bit. Okay, so here we have now C1H5N1, and you can also write this as CH5N. So this is the empirical formula. Okay, that's one thing. Now the question is asking us find the molecular formula, and what they have given is the formula mass, the molar mass. Okay, so we know the formula, that the empirical formula mass, so your empirical formula times some number, and that's going to give you the molecular formula. But what is that number? N is the molar mass that is given. Okay, so molar mass divided by the empirical formula mass. Okay, and sometimes it is okay to have the same, the empirical formula mass and the molar mass can be the same, but there can be also times when they are different. So you really have to calculate the molar mass of the coming from the empirical formula. Okay, so we have here, we are going to calculate that and something that is given to us. So let's look at this. So CH5N, that means 1 atom of carbon, 5 atoms of hydrogen, and 1 atom of nitrogen. Carbon is 12, hydrogen is 1, nitrogen is 14. And you are going to get 12 from the carbon, 5 from hydrogen, and 14. 10, 11, and 31 grams per mole. So this is the coming from the empirical formula mass. Okay, so just remember that this is coming from the empirical formula mass. Okay, but you are also given something. You're already given a molar mass in the question, given the molar mass in the question. Okay, in the question, and that is 31. That's already given to you, and that is also the same as the empirical formula mass, which is fine. So we were given 31.06 grams, 31.06 grams, okay, grams per mole, sorry, given in the question, and that is the molar mass. So you can easily take the empirical formula mass. Let's do this. So that is your empirical formula mass. Like next is the step 8. Okay, you take the empirical formula mass and the molar mass and divide them. And that's going to give you the value of N. So N is the molar mass divided by the empirical formula mass, and that is equal to, the molar mass is equal to 31.06. And so for now, it's safe to just use it 31, because we need the whole numbers anyways, over 31. So this value is 1. Okay, so next thing you're going to do is you're going to put this number in the same in the end. So empirical formula times the value of N, which is 1 in this case, is equal to the molecular formula. So in other words, CH5, so that's your last piece right here, is this 10. Okay, so we have the CH5N, which was the empirical formula, CH5N times 1. CH5N times the value of N, which is 1, is equal to CH5N. So this is also the molecular formula. Okay, so this is how you do this calculations when from the elemental analysis you are given carbon dioxide, you're given the values of water, you're given maybe ammonia. Now in case nitrogen is not given to you, then you can always convert the mass percentages as we talked about here. Once you get the mass percentages, you can minus the going to add the 2 components and minus them from the 100. So that's going to give you the third component. Okay, so these are the 10 steps, and again, it can be a little bit confusing, but just keep this picture in mind, then you will know where the carbon dioxide is coming from. But we're not really interested in carbon dioxide, we're not interested in water, we are only interested in carbon and hydrogen. And where is that carbon and hydrogen coming from? It's coming from the sample. Okay, and so we are trying to determine how much of that is there, and so that's where the empirical and the molecular formulas come into play. Okay, so with that said, I hope it was easy and helpful. All right, thank you so much, and bye-bye.